Very good morning. What we have done so far is we have considered the initial value problem and try to approximate its solution at values at x equals to xi's, where xi's are equispaced point from a to in the interval a to b with size h equals to b minus a by n. Okay, and then to approximate the solution, we have started with the Taylor's method. We have given that then Euler's method and then Taylor's method of higher order. Then we have also stated the Runge-Kutta methods of order 2 and order 4. Then we have also utilized the technique which we have learned during interpolation and numerical integration by integrating both sides over the interval xi to xi plus 1 and so on. Then we have estimated or approximated the integral on the right side by using rectangle rule, midpoint rule, trapezoidal rule, which adds with some methods, okay, which we have learned, and then try to approximate the solution of some of the examples. And one of the example we have seen that error is increasing exponentially there. So there was some issue in like a stability issue with this rule that we are going to see in this session. Okay, and we have also stated that Taylor's method or these single step methods are classical methods and they are always going to be stable. That also we will try to get the answer here. So to check the stability of different type of methods, we are going to use a very specific equation which is commonly known as test equation. Okay, so the test equation is given by y dash equals to lambda y with y at 0 equals to 1. And if you compare it with the original initial value problem, then you can get that f of xy is equals to lambda y. And that a is equals to 0 and y naught equals to 1. And you can see that that exact solution a can be derived by using variable separable methods, or this is a linear first order differential equation. You can find the integrating factor and you can solve it out. So this exact solution will be e to the power lambda x, and we have taken the interval x in the interval 0 to p. Then we have considered a uniform partition of this considered interval 0 to p. So here x0 is 0 and other points, interior points are defined xi as a plus ih, but a is 0. So xi is equals to 0 plus ih, that is ih. And then h is what? B minus a by n. So here a is 0, it is going to be b by n. So, and then xn equals to b. Okay, now we will try to explore the standard methods explicitly here. So let's first look the Euler's method, what it will give in this case of test equation. So we are going to use the considered problem as y dash equals to lambda y at 0 equals to 1, and we will apply the Euler's method, Runge-Kutta method of order 2 for this equation, and then we will try to come up with some conclusion. Okay, right. So here the Euler's method, if you look at, so that's going to be yn plus 1 equals to yn plus h time f of x and y. So that we have just now derived that f of xy is nothing but lambda time y. So lambda time with the second argument here. So this is going to be lambda time y1 yn. So yn plus h time lambda yn, that's going to be 1 plus h lambda yn. Now use this relation as a recurrence relation between yn plus 1 and yn. Then you keep on applying this. So then the next is going to be 1 plus lambda h square yn minus 1. Next will be 1 plus lambda h to the power cube time yn minus 2 and so on. So you can see that the superscript, or you can say power is 1 in the first case, and the suffix of y is n. So n is, the total is n plus 1. In the next also, 2 plus n minus 1 is n plus 1. 3 plus n minus 2 is n plus 1, so and so on. So what will be the last term will be 1 plus lambda is to the power n plus 1. You are going till y0, but you note that y0 value is 1. So this is going to be 1 plus lambda is to the power n plus 1. Okay, so let us hold on for a second and let's look the final expression for the Runge-Kutta method here. Okay, right. So what will be the Runge-Kutta method of order 2? So if I define explicitly that the expression for Runge-Kutta method is given by this equation, yn plus 1 equals to yn plus 1 by 2 times k1 plus k2. So where k1 and k2 are explicitly given by the following formulas. Okay, now use the fact that f of x comma y is lambda time y. So it is going to be f of x and yn is lambda time by n. And here h time f of xn plus h comma yn plus k1 is lambda time the second argument, that is yn plus k1. Now use the fact that k1 is h lambda yn. Substitute here. Then you substitute this k1 and k2 in the numerical scheme. Then what you will get is, so h lambda will come 2 times, so 2h lambda yn. So 2 will get cancelled, and the third term h square lambda square by 2 yn. Now yn is common in every term, so this is taken common, and what is remaining inside is 1 plus lambda h plus lambda square h square by 2. Now if you similarly as previously, as in the previous case we have done, we have used the recurrence relation to reach to till y0. So but y0 value is 1. So in the similar fashion, we are going to have the expression for yn plus 1 is going to be 1 plus lambda h plus lambda square h square by 2 to the power n plus 1. Right. So now we are going to look at the error in both cases. Okay. So you know that exact solution is e to the power lambda x. So if you replace x by nh, okay, so you will get the solution. So what will be the solution? Y at xn is going to be e to the power lambda xn. But what is xn is nh, so e to the power n lambda h. Okay, so this is this is going to be the exact value. Okay, now we want to make a difference with the exact value and the approximated value. So before going this, so we are going to look at this e to the power x in a very special form. So if you use the Taylor's approximation, so e to the power x can be expanded as 1 plus x square by 2 plus x cube by 3 factorial plus x4 by x power 4 by 4 factorial and so on. Okay, or you can truncate after the second term by using the Taylor series, that is going to be, see, we are looking for the Euler's method, so we are expanding for this case. So in this case, we require the of h square, right? If you recall, what was the local discretization error? Was of h square. So we are truncating after the second term here. Okay. Similarly, for the Runge-Kutta method, we will also use the similar concept here. Now, then what will be e to the power x can be written as 1 plus x plus of x square. Okay. Now, what will be the e to the power nx is going to be 1 plus x to the power n plus the higher order term x square. That can be verified easily. So now replace x by h lambda. So we have substituted x equals to h lambda on both sides. Okay, so that will give you that e to the power n h lambda is equals to 1 plus h lambda to the power n plus of h k lambda. But you know that for Euler's method, this is yn plus of h square lambda square, and the right side y at xn is equals to yn plus of h square lambda. So if you take this yn on the left side, that will give you the error term. So this is nothing but en, which is going to be of h square lambda square, which is the same as local discretization error in the Euler's method. Now, similarly, you can look at in the Runge-Kutta method of order 2. So instead of expanding till second term, we are going to expand it till the third term because we have to look for the error of h cube. So similarly, we are proceeding e to the power nx can be is equals to the 1 plus x square by 2 to the power n plus of x cube. Then you replace x is equals to h lambda, and then you can look that this is implies y at xn is equals to yn plus of h cube lambda cube. So this will give you that error is of big of h cube lambda cube. Now let's look at the midpoint rule now for the same test equation. So we recall what was the test equation is y at n plus 1 is equals to given by y n minus 1 plus 2h time f of x and y. Now use the definition of f of x comma y, that is lambda y. Okay, so f of x and comma yn is lambda time yn. Now yn plus 1 is equals to yn plus 1 plus 2h lambda yn. Now arrange all the things on the left side. So this is a difference equation of order 2. In order to solve this equation, you require two starting values. Okay, so one value is given to you, y0 is 1. So another values we will borrow from the exact solution. So for finding the unique solution, we are going to assign two conditions, or you can say two starting values, that y0 and y1 values. Okay, and then we will see what will happen with this. Okay, right. Now, so for unique solution, we need two values to start. So first condition is y0 equals to 1. So we know exact solution is y equals to e to the power lambda x. So then we will certainly have the another condition which is given by y1, which is y at h, that is equals to e to the power lambda h, which will give you second condition. Okay, now so this difference equation along with these two conditions will give you the unique solution. It is the same situation as you have in like first order differential equation. If you want to solve uniquely, you need to assign one condition. Okay, now similarly, if you want to solve second order differential equation uniquely, then you need to assign two boundary condition or two conditions to determine two constants. So similarly here, so it's a differential equation of order 2. So it requires two conditions at the starting to determine a unique solution. Okay, right. Now if so, we are going to substitute yn equals to r to the power n in the difference equation. Okay, so if we substitute, then what you will get is r to the power as y. So if you recall, what is the equation is yn plus 1 minus 2h lambda yn minus yn minus 1 is equals to 0. Now replace yn equals to r to the power n, means y at n minus 1 is r to the power n minus 1, and y at n plus 1 is equals to, at xn plus 1 is equals to r to the power n plus 1. This is the same thing like we have done for getting the solution of second order differential equations with constant coefficients. Okay, like we have substituted y equals to e to the power lambda x, and then we try to find the roots of the auxiliary equation. Okay, similarly here, means we are assuming that the solution is of the type yn equals to r to the power n for the given difference equation. Okay, so in that situation, what will happen is r to the power n plus 1 minus 2 lambda is r to the power n minus r to the power n minus. So which turns out to be, so if you take this LCM and rearranging or simplify this, what you will get is r to the power n out. Okay, then not that we are not interested in the zero solution. Okay, so this r to the power n is a non-zero now. Okay, so this is r to the power n is gone this right side, and then we have left with the following quadratic equation in R, which gives you two solutions for this. So R1 and R2, which can solve uniquely. Now, so when you have these, so two values, so the general solution will be the linear combination of the solutions, two solutions. So one solution is R1 to the power n, another solution is R2 to the power n for the difference equation. Okay, so general solution will be the linear combination of them. So these arbitrary constants can be obtained by using the given conditions that y naught equals to 1 and y1 equals to e to the power lambda h. So use the first condition. Using the first condition, y naught equals to 1. What it will imply is, so y naught means n equals to 0. Okay, so when you have put n equals to 0, so r1 to the power 0 and r2 to the power 0 is 1. So this will give you beta 1 plus beta 2 equals to 1. And similarly, y1 equals to e to the power lambda h. So at n equals to 1, that will give you the e to the power lambda h. So what we will have is the following: y naught equals to 1 implies this, and y1 equals to e to the power lambda h implies this. Now, also note that R1 values are also obtained. Okay, so let's have this R1 values noted. Now you can solve these two equations in two unknown, right? In beta 1 and beta 2. Okay, at that you can get the, then you can get the beta 1 and beta 2 value uniquely now. Okay, right. So from here, if you look at now, beta 1 plus beta 2 equals to 1 implies beta 2 equals to 1 minus beta 1. Now, we are going to substitute this in this equation. And what it will give you on simplifying the first term as it is plus R2 times beta 2. Beta 2 is 1 minus beta 1 is equals to y1. So now arrange the coefficient of beta 1 on the one side, left side, and rest you can send it on the right side. Okay, and then what you will get is beta 1 equals to y1 minus r2 divided by r1 minus r2. Now look at the definition of r1 and r2. Okay, so if you look at here, so this implies r1 minus r2 will give you, so difference, this lambda h will get cancelled, you will get 2 times square root of 1 plus lambda square h square. Okay, and what is r1 value is lambda h plus square root of 1 plus lambda h square h square, and r2 value is lambda h minus square root of 1 plus lambda square h square. Okay, so we replace r2 by the value. Now what will happen now? So you can use this now, e to the power lambda h, y1 is what, e to the power lambda h minus r2 value divided by r1 minus r2. Now we can, this is kind of a plus b divided by some denominator, so that's a by this plus this by this. So this will give you, the second term will be 1 by 2, the first term will be e to the power lambda h minus lambda h divided by 2 square root of 1 plus lambda square h square. Now as h tends to 0, so if you take h tending to 0, what you will get is the second term will converge to 1 by 2 only in the limiting case. And what about this? So the second term here, if you look at as h tends to 0, this tends to 0. This tends to 1. And the denominator converges to 2. If you look at carefully, see, you have, this is like xn by yn. So both converges. So suppose limit xn exists and limit yn exists. And suppose limit of yn is non-zero. Then the limit of xn by yn is x by y. Okay, so we are going to use that factor. So the numerator limit is 0, oh, sorry, 1, and denominator limit is 2. So it will definitely converge to 1 by 2. So the limit will converge to the total limit will be 1 by 2 plus 1 by 2, that is equals to 1. So this gives you that beta 1 goes to 1 as s tends to 0. If you take h as small as possible, so beta 1 is going closer to 1. Now, once beta 1 is going to closer to 1, so but what is the definition of beta 2 is 1 minus beta 1. So as s tends to 0, beta 2 going to 0. Okay, right. So this is what had happened now. Beta 2 goes to 0 as s tends to 0. Now what we are going to look for is we are going to we are having R1 expression and R2 expression. Okay, and we are having R1 expression is having square root of 1 plus lambda square x square, and R2 also have the similar. So we want to get rid of this by replacing some of the approximation of it. So what is the similar function we can look here is square root of 1 plus x function. F of x equals to square root of 1 plus x. So you know that this function is differentiable. So x is any, you can say greater than equals to 0 now. So this function is continuous and differentiable. And then fundamental mean value theorem implies the following. So this will give you that establish that f of x can be approximated by 1 plus x times f dash of c. That is going to be 1 plus of x. Okay, right. So with the use of this, we can replace R1 and R2 as follows. So R1 was lambda h plus square root of 1 plus x square lambda square. Now square root of 1 plus x can be replaced by 1 plus of x. So 1 plus of h square lambda square. Similarly, R2 is lambda h minus 1 plus of h square lambda square. Okay, right. Now look at the powers now. In the similar manner, how we have looked for e to the power x. Similarly here, so r1 to the power n will be 1 plus lambda s to the power n plus of h square lambda square, and r2 to the power n is lambda h minus 1 to the power n plus of h square lambda square, which you can write as minus 1 to the power n is out and 1 minus lambda s to the power n. Okay, right. So this will implies yn equals to beta 1 time r1 to the power n plus beta 2 time r2 to the power n. Okay, so now substitute r1 to the power n here and r2 to the power n here. So what you will get is you have beta 1 time 1 plus lambda h to the power n plus beta 2 time minus 1 to the power n time 1 minus lambda h to the power n plus of h square lambda square, right? Okay, now this we have already established the following. So we have already established that e to the power nh lambda can be approximated by 1 plus lambda h to the power n plus of h square lambda square in the when we are dealing with the Euler's method. In the similar fashion, we can also show that e to the power minus n lambda h can be approximated by 1 minus lambda h to the power n plus of h square lambda square. Okay, so this again you are going to replace this by the following approximation now. Okay, then what you will get is the following shape. Now what you can look now here. Now suppose lambda is greater than 0. Okay, suppose lambda is greater than 0. Then what will happen is then the things are okay. Why? Because as n goes to infinity, okay, then this will not dominate the solution. But if lambda is less than 0, then this becomes positive, and this will dominate the true solution. But because the true solution is given by e to the power lambda x, so you know that the first term will corresponds to the true solution, but the second solution will not create any problem as far as lambda is greater than 0. But once lambda is less than 0, then this solution will actually dominate the true solution, and therefore error increases here exponentially. So this solution also known as extraneous solution. Okay, right. So this established that midpoint rule have some stability issue. Okay, and that is with respect to here is lambda greater than 0 and lambda less than 0, that can be checked. So in the considered problem, uh, if you look at back and look at the equation, what was that? Y dash equals to minus 2y plus 1. So lambda is minus 2. So that is less than 0. So therefore, your extraneous solution start dominating the true solution, and you are getting the error increases exponentially there. Okay, fine. Right. So now the next we are going to consider the boundary value problems. Okay, and we try to see how do we approximate the solution for them. Right. Now, so as told previously, we are going to consider the second order differential equations with variable coefficients or constant coefficient. Okay, with two conditions, y at a is equals to alpha and y at b equals to beta. Here the notations y dash stands for first derivative of y with respect to x, y double dash stands for second order derivative of y with respect to x. And we have assumed that x lies between the interval a to b, and at the left hand point and right hand point the values are given alpha and beta. Okay, then also further we have assumed that these coefficients p of x, q of x and the right side are continuous functions on closed interval ab, which essentially gives the guarantee that this equation has unique solution. Okay, this has unique solution. Okay, so this due to this we have made this assumption. Okay, now what we are going to next is we are going to replace the y by the approximated value y at xi, and y dash and y double dash are going to be replaced by their approximation. So we are going to use the technique which we have learned in during the numerical differentiation class. Okay, so we have replaced the first order derivative or second order derivative by using forward difference operator or backward difference operator, or if you want more good accuracy, then you can also use the central difference operator. Okay, so for doing all these things, first we are going to consider the uniform partition of the closed interval AB. Means we are going to divide this interval into n subintervals. Okay, where length of each subinterval is equals to h. Okay, right, fine. So for approximating solution of one, we consider the following uniform partition. Now, since one holds true for each x, so if you look at this equation, this is true for each x in the interval a to b. So therefore, it is also hold true for every point inside AB. Okay, so it also holds for true for at the partition points. Okay, so at the partition points x0, x1, x2, xn. Okay, so x1 to xn minus 1 are called interior points. Since we have the values, already have the values at a, and I also have the values at b, so we are only going to consider the equation at which involves x1 to xn minus 1. Okay, so now since one holds true for each x in AB, so it also holds true for each xi. So you can replace x by xi is how, you know. So y double dash at xi plus p at xi into y dash at xi plus q at xi times y at xi is equals to r at xi. Okay, so this remains true. Okay, so as from 1 we have the following. So replace x by xi in the original equation. Now as already mentioned, at x naught equals to a and at x naught xn equals to b, we know the values of y. So therefore we are considering only interior part. So this equation we are only considering here n minus 1 number of equations. Okay, now idea is replace the second order derivatives and first order derivative by finite difference. So as told, you can use forward difference operator, backward difference operator, or central difference. Right? So we are going to use here central difference operator for the y dash and y double dash. Replacing this. Okay, right. Now, if you recall f dash, how it is related with the forward difference operator is given by delta fxi yh. Okay, and which is given by f of xi plus match minus f of xi, means future value minus present value. Also, it is related with the backward difference operator by this. So f of xi minus f of xi minus h by h, means present value minus past value divided by h. And if you want to use the notation, this is nothing but fi plus 1 at I plus 1th point minus at ith point divided by h. If you look write down in the discretized notation, that is fi minus fi minus 1 divided by h. And this is fi plus 1 minus f minus fi minus 1 divided by 2h. Okay, so these are the definitions of central difference and backward difference in this. They are related with the first derivative by the following relation. Okay, and note that the central difference operator is using the symmetric with respect to the midpoint xi. Okay, now similarly, second derivative. Second derivative also is also related with the forward difference. You can also find, okay, the relation, okay, that we have already discussed in the numerical differentiation class. Okay, and since we are going to use the central difference, we are going to use the following relation at the end. So these are the expansion by using the central difference and forward difference operator 2 times, backward difference operator 2 times, and central difference operator 2 times about the point xi minus h, and xi plus h here. Okay, so if you want, so here you have followed that similar definition that you can get it from the. You just write down the steps. You can get these results easily. Okay, right. So using these facts, so we have the equation I equals to for I equals to 1 to n minus 1, the following equations. Now replace y at xi by yi. Then y dash at xi by the central difference y at I plus 1 minus y at I minus 1 divided by 2h. And second derivative by using central difference again. So yi plus 1 minus 2yi plus yi minus 1 divided by h. Okay, so that these things we have already deriven previously in the numerical differentiation session as well. Now, once you replace them, so y double dash is replaced, y dash is replaced, and y at xi is replaced. Okay, then we will arrange the coefficients of yi plus 1, yi, and yi minus 1 on the one side, and rest of the things we will send it on the right side. Okay, right. So once you replace, so I have replaced here. So it is replacement of y double dash. This is replacement of y dash, and this is y. Now on simplifying, so yi minus 1 coefficient is 1 by h square. Here right? So now what you can do is first multiplying both side by h square, and then we try to rearrange the coefficients of yi minus 1, yi and yi plus 1. So if you multiply by h square, so here the coefficient of yi minus 1 is remain 1, and here p of xi, 2h is there, so by 2 h time pxy by 2 with minus sign that is going here. Similarly, if you see the look at the yi coefficient now, it is minus 2 from the first term, and from the second term there is nothing. From the last term you have q of xi into h square. Now similarly the coefficient of yi plus 1. So here the coefficient is 1 because h square is on in the right side, and from here yi plus 1 it is again p of h time p of xi by 2, so with plus sign. So these are the coefficients of yi minus 1, yi and yi plus 1 is equals to h square time rx. So you have n minus 1 equations. Okay, in how many unknowns? We have y1 to yn minus 1. So in n minus 1 unknowns. Okay, right. So which you can write equivalently in the form of system of equation, matrix representation also you can write. Okay, so for the sake of simplicity, we let this ai to be yi minus 1 coefficient, di is yi coefficient, and ci is the yi plus 1 coefficient. So, and we will use the fact that that conditions y at a is equals to alpha and y at b is equals to beta. Okay, right. So for I equals to 1, if you replace I equals to 1 here, so what you will get is, so this is, we have used this, the notation is AI. This is the notation we have used is DI. This notation we have, for this we have used the CI notation. We are going to replace I equals to 1 in the original equation. So if you replace I is equals to 1, what you will get is, the first term is I is equals to 1, so A1 y naught plus D1 y1 plus C1 y2 is equals to h square r at x1. Now, since y naught value is known to you, that is equals to a, right? So that is equals to alpha. So that can be sent on the right side. So that will so simplify is d1 y1 plus c1 y2 is equals to h square time r at x1 minus a1 alpha. So this is what you have got the for the condition I equals to 1. Similarly, for the condition I equals to n minus 1, what you will get is, for the condition I equals to n minus 1, so if you replace I equals to n minus 1, so what you will get is an minus 1 yn minus 2 plus dn minus 1 yn minus 1 plus cn minus 1 yn is equals to h square time r at xn, r at xn minus 1. Now, since y at n is not, y at xn is nothing but y at b, and that is nothing but beta. Okay, so you can send this last term on the right side, and then you can write the simplified form as an minus 1 yn minus 2 plus dn minus 1 time yn minus 1 equals to h square time r at xn minus 1 minus cn minus 1 beta. Okay, so this is what the second equation gives you. Now you have n minus 1 equation in n minus 1 unknowns. Now keep all the things, okay, and then write the equivalent matrix form. So these are the following three equations now. So for I equals to 1, you have the first equation. From 2 to n minus 2, you have the following equation, and for this I equals to n minus. Now you can write down the equivalent matrix form as well. Okay, so if you look at carefully, okay, the first column will be D1 C1 and rest of the terms are 0. Okay, so let's see the D1 C1, rest of the terms are D1 C1, rest of the terms are 0. The unknown vector is y1 to yn minus 1 equals to right hand side. The first row is h square r1 minus a1 alpha. Now, if you look at the second for I equals to 2. Now, for the I equals to 2 is a2 y1, d2 y2, c2 y3 is equals to h square time r2. So if you replace I equals to 2, so a2, d2, c2 will be at the position first, second and third, and the rest of the terms are 0 because they are the coefficients of y1, y2, y3. Okay, and the right side is h square r2. Similarly, so it will be transformed into a tridiagonal system. So you will see this will be in the form of tridiagonal system, which can be solved by using the methods for solving system of linear equation, which you have. So similarly, the last equation also you can copy, okay, from in the put down carefully in the matrix form. Okay, so now let's take an example here and try to address the problem. Okay, so let's take this example. The y double dash plus y equals to 0 with the initial condition, with the boundary conditions are y at 0 equals to 0 and y at 1 is 1, whose exact solution can be verified that this is sine x by sine 1. So you can verify that at x equals to 0, sine 0, y at 0 is 0, y at 1 is sine 1 by 1, that is 1. So the boundary conditions are satisfied and you can show that this actually satisfies this equation because sine x function is a harmonic function. Okay, right. Now if you compare with the standard equation, you can extract the p, q and r from there. A value, B value, alpha value and beta value. So if you compare y dash coefficient, that is 0, there is no y dash. Qx is y coefficient, that is 1. Rx is the right side, is 0. A is the at the left hand point, that is 0. B is the right hand point, that is 1. So A is equals to 0, B equals to 1. And alpha and beta are the values at A and B, that is 0 and 1 respectively. Now we are going to compare it with the corresponding difference equation. So then if you recall what was an and cn was, if you recall what was an and cn values is an was 1 minus h by 2 p at xi and cn was 1 plus h by 2 p at xi. If you compare, and what was the dn was minus 2 plus h square q at xi, if you recall. Okay, so these are the values ai, ci and di. So when p is 1, sorry, p is 0 and q value is 1 for the given equation. So that will give you that ai is equals to ci is equals to 1. Okay, and di is equals to h square minus 2. Then the system of equation you can write in the following. And the right hand side you can now match with the alpha is 0 and beta is 1. Okay, and r function, right hand side function is 0. So you will only all the values on the right side is 0 except the last one, that is going to be minus beta, that is minus 1. Okay, right. So this is the system of equation you will obtain. So let's fix some value of h and try to solve this out. Okay, so let n equals to 4. So this gives you h equals to b minus a by n. That is going to be 1 minus 0 by 4. That is going to be 0.25. Now replace h value by 0.25. So you will get n equals to 4. Means you have y0, y1, y2, y3, and y4. We are going till 5, 4. But now, since y0 and y4 are known to you, these are only unknowns. So n equals to 4. So it reduces to the following form. The system will reduce into the following form. If you carefully fit all the values, okay, only you need to get is h square minus 2. Okay, right. Now we will try to make these 0, and then we will use the backward substitution method. So we have used the simple methodology, but we have used during the cost elimination method case. Okay, and what we will, so we first use the operation as R2, change it to R2 plus 1 by 1.9375 R1. So here is the multiplier is 1 upon 1.937. Okay, for the next case, the multiplier is 1 upon 1.42134 to the second root. And then what it will be transformed into this upper triangular system, and that can be solved by using the backward substitution method. Okay, so you got the approximate solution. So you can definitely compare with the exact values. So exact values are also obtained by using the calculator now. Okay, and then you can compare that they are not very far from the exact solution. Okay, right. So you can increase the value of h, or sorry, you can increase the number of partition points, or in other words, you can reduce the size of h to get more accuracy here. Okay, but if you reduce the h, then what will happen is the size of the matrix will increase. Okay, and then means like it will become computationally very costly. So if you take h very small, it will be a huge order matrix. Okay, and then there are issues of how to make it computationally effective and less costly. Okay, right. So there this improvised method will come into the picture, which is known as finite element method. Okay, but this is beyond the scope of this course that we are not going to discuss here. Okay, so okay, so we are going to end with the session now. Okay, thank you.